Okay, welcome back. So in this second lecture, in this short series, we're going to look again at the SIR model, but now we're focusing on the mathematical properties of the SIR model. So this is, believe it or not, this is a simple model. And because it is relatively simple like this, we can do a lot of mathematical analysis. And okay, it's interesting for its own sake, but I promise you this analysis will give us much better understanding of the dynamics of disease outbreak. So that's the aim of this short lecture. Mathematical analysis plus a bit more understanding of disease outbreak, in particular the dynamics. So, you know, how the outbreak evolves over time. So the initial conditions are S at time 0 is S naught, I at time 0 is I naught, and the number of recovered at time 0 is 0. So S naught plus I naught sums to N, the total population. And in this lecture, we're working from sections 3.2 and 3.3 from the type notes. So this equation 1 here is remarkable in that this set of equations, in that it can be reduced down to a single ODE. And this is a quite an unusual feature of the SIR model. Other more complicated models for disease outbreak don't have this feature. It's just luck, really. So we're going to reduce this set of coupled equations, the 3-equation model in equation 1. We're going to reduce it down to a single ordinary differential equation, or ODE. And now I show you how. So the first step is to look, first of all, at the S and the R equations. So ds by dt is minus beta over n times si, and dr by dt is gamma times I. So I combine these two equations. I've got ds by dt is minus beta over n times s. And now instead of I would write I equals 1 over gamma dr by dt. So this is my I. And I have a d by dt on both sides, and I can so-called formally cancel these. So it's like treating the dt's as algebraic objects, which can be cancelled. We know this is not correct. It can be made correct using chain rules and so on. But just to save time, we can say we're formally cancelling the dt's. And this leaves us with ds equals minus beta over n times 1 over gamma times s dr. And I divide across by s to get ds over s is minus beta over gamma times 1 over n times dr. And I now integrate, because this is an ordinary differential equation, I integrate from t equals 0 when s is s naught and r is 0 out to a finite time when s of t has some value s and r of t has some value r. So I get this integral ds over s is minus beta over gamma times 1 over n, which is constant, times the integral of dr. So the integral on the left-hand side is log s minus log s naught is minus beta over gamma times 1 over n times r. So s is equal to s naught, I exponentiate, take exponentials on both sides. S is equal to s naught e to the minus beta over gamma 1 over n times r, which, just to save time, I relabel as u. So u is beta over gamma 1 over n times r. S is s naught e to the minus u. Okay, so that's step 1. Step 2 is to use the fact that s plus I plus r is equal to n, which is a constant. So from equation 2, I is n minus s minus r, just rearranging, but s now is s naught e to the minus u. This is I. I will sub this into dr by dt. So this new formula for I. So dr by dt is gamma times I, which is now n minus s naught e to the minus u minus r. And u is really just r in disguise. So I take this equation here and I multiply both sides by beta over gamma times 1 over n, because this combination will just be u. So multiplying across, by beta over gamma times 1 over n. The first term was gamma times n, and it now gets multiplied by beta over gamma times 1 over n. And the n's cancel, and the gammas cancel. The next term would be gamma times s naught times e to the minus u, and it's now being multiplied by beta over gamma times 1 over n, so the gammas cancel. And the third term was gamma times r, and this is now getting multiplied by beta over gamma times 1 over n. And I'm just going to group this together because this is u again. So grouping things together and identifying u, I get du by dt is equal to beta minus s naught over n times beta times e to the minus u minus gamma times u. And I actually want, I mean, this is one equation now. Everything just involves u. But I do want to do one more step. And this just helps us with the analysis later on. So I actually divide out by s naught over n times beta. So I've got du by dt, and I'm dividing out by s naught times beta over n. The first term, I started off with a beta, and now downstairs I have an s naught times beta, and upstairs I have an n. So the betas are actually cancelling here. The second term, I had an s naught times beta over n upstairs, and I now have the same thing downstairs, so above and below cancel, and it's just 1 in front of the exponential. And lastly, I had u times gamma, and now I have a beta times s naught downstairs and an n upstairs. So I identify some new variables here. I identify a rescale time, and this is somehow dimensionless. So I identify the downstairs over here with d tau, and this is s naught over n times beta times dt. And you see s naught over n is people over people, so that's dimensions of 1. Beta is 1 over time, and dt is time, so this has dimension of 1 as well. So d tau is a dimensionless variable. I also have, in this scaled equation, I have a factor of n over s naught, and I call that a, and I can say for straight away that that this is greater than 1 because n is equal to s naught plus I naught, and then this is divided by s naught. So this is 1 plus I naught over s naught, and we always have at least a patient 0. So this is greater than 1. And then crucially, I have this grouping of parameters. I have a beta s naught and I have a gamma n. So I identify parameter r naught, which is beta over gamma times s naught over n, and I'll call that 3. So now my scaled equation becomes 4. Du by d tau equals a minus 1 over r naught u minus e to the minus u. So this is reducing everything down to a single equation. So if you like, this is a nice mathematical exercise, but there's more to it. And here's why. This exercise enables us to learn some key concepts in mathematical epidemiology. And for this reason, we're going to look at section 3.3 of the type notes. So we're going to analyze this equation 4. And it's just better to look at it in this way, that it's du by d tau equals f of u. F of u is the right-hand side, a minus 1 over r naught u minus e to the minus u, equation 5. So what we're going to do here is we're going to look at the equilibria of equation 5. In other words, solutions of the equation that are just constant over time. So u is a constant, and we'll just call it u star. So if it's a constant solution, du star by dt is 0. But u star has to satisfy the equation, so du star is f of u star. So also f of u star has to be equal to 0. So these equilibrium solutions, they satisfy f of u star equals 0. And so finding the equilibrium solutions is just reduced down to a root finding problem. So we need to find the roots of f of u equals 0. And here I do that by a graphical method. So I'm just going to plot f of u as a function of u and find out where this crosses the horizontal axis. And so, yeah, we have to plot f of u, and I can show you some tricks for how to do a rough sketch of f of u. we first of all look at the behavior of f of u near 0. So I do a little Taylor expansion. So f of u is well approximated by f of 0 plus f prime of 0 times u near u equals 0. So f of 0 is a minus 1, and this is strictly positive because a is greater than 1. And I just compute the derivative. And I have f of u written down here, so we can just compute the derivative and evaluate at 0. So we can do that yourself in your head, evaluate at 0, and you get this. So f at 0 is strictly positive. That's the first observation. We also look at the behavior of f of u as u goes to infinity. So as u goes to infinity, this term goes to 0, and then this goes to infinity, so this goes to minus infinity, so this term dominates. And so f of u goes as minus 1 over r naught times u, as u tends to infinity. So we can say that f of u tends to minus infinity, as u tends to infinity. We also look at maxima and minima of f, so we want to look at f prime of u equals 0. And again, looking at f of u, this corresponds to looking at 1 over r naught equals e to the minus u. So u will be log of r naught. But u is a kind of scaled population, so it has to be a positive number. So u has to be positive. So for f to have a max or a min, r naught has to be greater than 1. And we just double check, we evaluate f double prime, and it's minus e to the minus u. So whatever value u has, this second derivative is negative. So by the second derivative test, u equals log of r naught is a maximum. And we can now sketch f of u. And remember, we have to take u greater than 0, so the half line, because u is a scaled population. And we see there are two possibilities. We're always starting with f of u equals a minus 1. If r naught is greater than 1, we have a maximum, so we go up before going down off to minus infinity. If r naught is less than 1, we go down to minus infinity from the get-go. So in both cases, we see that the curve crosses the horizontal axis in just a single place. So there's only one root, one equilibrium solution, also called a fixed point. And again, the same thing is plotted here, and this is just taken directly from the type notes. So let's have a look again, just briefly at this case when r naught is greater than 1. Then f of u has a peak. At the peak, the first derivative is 0, but also dr by dt is proportional to f, because, you know, du by d tau equals f of u, and this will be proportional to dr by dt. So the second derivative of r with respect to t, just doing the chain rule, you know, if I do d by dt of f, it will be f prime of u times du by dt. So, and du by dt is f, or at least proportional to f. So d2r by dt squared is proportional to f prime times f. F prime is 0 at the peak. So at this peak, d2r by dt squared is 0. So for r naught greater than 1, if we start with an initial condition, u naught equals 0, so no recovered individuals at time 0, the number of recovered people accelerates. So the second derivative is positive. At the peak, the acceleration stops, and then after the peak, this number decelerates. So on the other hand, if r naught is less than 1, you get deceleration from the get-go. So there's this key observation that this threshold value, r naught, well, it's called the threshold. If r naught is greater than 1, this outbreak accelerates before slowing down. Whereas if r naught is less than 1, the outbreak decelerates from the get-go. And when you get this acceleration, when the outbreak, speeds up before slowing down, that is technically an epidemic. So we'll have one more way of looking at this. So we've got R naught again, and we need R naught greater than 1 for an epidemic. So how do we make R naught large? We can either make beta over gamma large. And remember, this is a ratio of rates. So if we try to make beta over gamma large, it means the infectious person stays infectious for a long time compared to the time it takes for recovery. Or I should say, the person is infecting a lot of people before he recovers. Alternatively, if we want to make R naught large, we can make S naught over N large. And in this case, it means there's a large pool of susceptible people present at time 0. So this number is the dreaded R naught, or the basic reproduction number in epidemiology. And I accept that maybe this metaphor with acceleration might be a bit confusing unless you have this background in mechanics and Newton's laws. I find it a helpful metaphor. Maybe it's not, but I promise in the next few lectures we'll do some numerical simulations of SIR models, and you will genuinely see from those that this R naught equals 1 is a threshold, and when you cross this threshold, the simulations do very different things. So we'll have a look at those simulations in the remaining lectures.